The Blackburn Meadows Renewable Energy Plant is a brownfield development by E.ON Climate and Renewables, close to the city of Sheffield in the United Kingdom. The site was formerly a coal-fired plant, which was decommissioned in the 1970s. Andritz received the contract from E.ON Climate and Renewables in November 2011. Andritz's scope encompassed the electromechanical power plant equipment, except the external fuel handling, the turbine generator unit and the high-voltage part. The EcoFluid AC boiler has a design heat input of 96.9 megawatt thermal, firing recycled wood, which produces 119 tons per hour of superheated steam. The comparatively high steam parameters of 490 degrees Celsius and 83 bar gauge at the boiler exit. Firing recycled wood is achieved by following a successful design concept with superheater wings in the second boiler pass. The boiler has a guaranteed efficiency of 91.9% at the design point. This results in a gross electrical output at the turbine generator of 33 megawatts at design conditions. The boiler design is tailor-made for a fuel with higher corrosion tendency, like recycled wood, with its higher heavy metal and chlorine content. The arrangement of the heating surfaces is carefully selected so that the corrosion risk is minimized, which is confirmed by similar applications. The plant will comply with the emission limits set by the Department for Environment, Food and Rural Affairs guidance on the European Waste Incineration Directive 2000/76/EC. As a leading worldwide supplier of fluidized bed combustion plants, the reference list of Andritz comprises more than 80 steam generators with capacities from 9 tons per hour to 400 tons per hour, with a fuel range from coal, biomass, sludge, RDF to various industrial wastes. The combustion system, bubbling fluidized bed or circulating fluidized bed, is selected according to the specific requirements of the various fuels and the required size of the boilers. Besides, the Blackburn Meadows project is an example of Andritz's experience in designing the electrical and mechanical balance of plant. The applied combustion technology is the EcoFluid bubbling fluidized bed. The main feature of this technology is the principle of staged combustion of the fuel. The oxygen level in the fluidized bed is limited, and hence only a part of the fuel is combusted, whereas the rest of the fuel is gasified. This can be achieved by adding only a substoichiometric amount of oxygen, approximately 0.35 lambda, to the fuel. In order to maintain the fluidization at an optimum level, at part load conditions, and when firing fuels with high heating values, for example, to necessitate less primary air for combustion, recirculation gas is added to the fluidization air. The substoichiometric bed operation allows the control of the bed temperature in the range between 650 degrees Celsius to 850 degrees Celsius. Therefore, also solid fuels with low ash melting temperature can be burned without any sintering problems in the bed. The standard operation temperature of the fluidized bed is approximately 760 degrees Celsius and can be maintained in a close range by controlling the ratio of primary air to recirculation gas. The gasification gases rising from the bed are fully combusted by injecting secondary air into the post-combustion chamber. This causes a rise in temperature and oxygen content, as seen in the diagram. The turbulence in this area of the first pass results in very low CO values in the flue gas. For high calorific fuels, recirculation gas is injected above the secondary air to cool the flue gases in the post-combustion chamber. The Blackburn Meadows plant is based on the bubbling fluidized bed technology, firing recycled wood. The steam is expanded in a steam turbine to produce up to 33 megawatts of electric power, and is then condensed in an air-cooled condenser. Up to 25 megawatts thermal of heat can be extracted from the turbine to the district heating system and supplied to nearby heat consumers through the associated district heating network. The plant design was based on the following design parameters, with the exception of the NOx value, which was set lower by the local authorities. The plant is designed to use two types of fuel, either recycled wood or light fuel oil for startup or shutdown and in case of loss of fuel supply. The Andritz scope of supply for the plant consisted of the following subsystems: an internal fuel feeding system, a fluidized bed steam generator, a combustion air system and burners, bed material and ash handling, ash silos and ash discharge, steel structures, stairs and platforms, emission control including selective non-catalytic reduction, bag filter and continuous emission monitoring, a stack, a water steam cycle with air-cooled condenser, extraction to district heating system, demineralized water plant and pressurized air system for the power plant, electrical balance of the plant, including cabling, MCCs, transformers and lighting, automation and instrumentation for Andritz's scope of supply, overall DCS and central control room, heating and ventilation. The steam generator is designed for the following data. The steam generator is a bottom-supported 3-pass type with natural circulation, where 3 passes are integrated in the evaporator water walls. The economizers are located in the 4th pass. The bubbling fluidized bed is situated in the lower part of the first boiler pass. The water walls in the fluidized bed area and a part of the post-combustion chamber are covered with refractory material for erosion protection and thermal reasons. The primary air enters the bubbling fluidized bed via the open-type air distributor. In order to maintain an optimum fluidization of the bed and a constant bed temperature, recirculated flue gas is added to the primary air upstream the air distributor. The concept warrants that the flue gas is cooled down sufficiently before it enters the first superheater bundles in the 3rd pass. The internal fuel handling system is based on Andritz's proven RDF feeding concept, which warrants highest availability. The recycled wood stored in the day silo is loosened by a rotor and subsequently falls into the troughs of the discharge screws, which discharge the fuel into one of 3 dosing bins. These dosing bins, together with the dosing screws, serve as an airtight seal to the boiler. Double screw conveyors extract the fuel out of the dosing bin. The DCS controls the speed of these double screw conveyors as a function of the boiler load. Finally, the fuel is injected via air-supported injection ports onto the fluidized bed. For the startup of the fluidized bed boiler, 4 burners are installed. Usually, the injection of coarse material like stones, nails, screws and metals cannot be entirely avoided. But with a properly designed nozzle grid, their negative effects like agglomerations in the bed can be significantly reduced. Andritz's proprietary design of the open nozzle bottom ensures that the coarse particles are constantly removed, and thus the optimum particle size fraction can be maintained. The air-cooled nozzle bars are positioned in such a way that the extraction even of larger particles is facilitated over the whole bed area. These nozzle bars are designed to avoid the clogging of the bed by wires and metal strips. This design has proven reliability at the hardest conditions, like the combustion of treated waste. After signature of the main contract in November 2011, the design of the district heating system was agreed and also became part of Andritz's scope of works. The steam is expanded in the steam turbine and is then condensed in an air-cooled condenser. A steam turbine bypass is installed for process setups and startup. The heat is extracted via 2 heat exchangers set at different pressure levels. In part load, the bleeds to the heat exchangers can be switched in order to adapt to the heat load requirements. A selective non-catalytic reduction system is installed in the post-combustion chamber. There, a water-urea mixture is injected into the flue gas, reducing the nitrogen oxide content. The staged combustion process itself is controlled in such a way by the combustion air distribution and the recirculated gas injection that no temperature peaks in the post-combustion chamber occur, which otherwise would increase the raw gas nitrogen oxide content. Any potential dioxin precursors are destroyed by maintaining a flue gas temperature above 850 degrees Celsius for more than 2 seconds, downstream of the injection of the secondary air. This requirement from the Waste Incineration Directive 2000/76/EC is fulfilled in the range described in the diagram. Activated carbon is injected downstream the economizer, reacting with all kinds of heavy metals, dioxins, and furans. The reaction products are extracted downstream in the bag filter. Upstream in the bag filter, a sorbent is injected, which is a highly active hydrated lime due to its highly porous reaction surface. Hydrogen chloride and sulfur oxide react with the sorbent in the flue gas duct, and mainly in the filter cake directly on the filter bags. The bag filters extract the reaction products and the dust. These are collected by screw conveyors and are sent periodically to the flue gas tank residues silo. Andritz is a globally leading supplier of plants, equipment and services for hydropower stations, the pulp and paper industry, the metalworking and steel industries, and for solid liquid separation in the municipal and industrial sectors. The publicly listed technology group is headquartered in Graz, Austria, and has a staff of approximately 24,500 employees. Andritz operates over 250 sites worldwide. For further inquiries regarding the Andritz Group and our products and services, please see our corporate website at www.andritz.com.